Hello, the Catbots presents the Bistro Bots, with team members being Elijah Hoffman, Tom Salona, Mitchell Graham, and myself, Jonathan Jesse. Restaurant owners have a very small profit margin to operate restaurants. The owners need a robotic system to enhance their service quality and to also reduce labor costs. Those that would be considering to buy the Bistro Bots would be the restaurant owners, servers, cleaning staff, managers, and investors. Others that would be interested in bistro bots would be those from the Food and Drug Administration, health inspectors, and OSHA. The table cleaning robot is done by Elijah Hoffman. The transport food robot is done by myself, Jonathan Jesse. The refill drinks robot is done by Mitchell Graham, and the dirty dish collector robot is done by Tom Salona. I completed the food transport robot. This robot will be tasked with the duties to transport food and utensils. Once the robot receives a command from the central hub, the robot will complete the task and then return back to the station. The circuits shown here uses three proximity sensors, two servos for movement of the arms, two DC motors for mobility, and this is powered by two 9-volt batteries. Here you can see the 16 centimeter wheels, two servo motors, and the LED command hub. On this slide, you can see the flow chart. Once it receives the command, the robot will move forward. Once a sensor senses the zone, it will use the arm to deliver the food and then return back to the start. And this is a Tinkercad in motion with the code.
My name is Mitchell, and I built the water refill robot. As the mechanical design, you can kind of see here. So my final rendering seems to have glitched in Tinkercad. Some of the transparent portions that I had to show some of the parts are no longer transparent. I tried working on that this morning to get it to work. Unfortunately, it wouldn't. But and as well as the motors that I had on the bottom of the robot disappeared, and I wasn't able to rescale them and get them down to size to fit this. So I just put on these red shapes here to kind of show these where the motors would go to control the wheels, the forward and backward and turn. I have this middle portion here of the robot. It was originally clear, as well as the top portion to show the tank, the water tank. But the middle portion was clear to show this is where the Arduino would go, as well as the spout. The servo motor was going to go inside here, or will go inside here, that controls the water flow. Yeah, in general, most of it would have been hidden inside the body of the machine. So this is kind of how it would look, except with a clear tank. The circuit, you can kind of see here, just grabbed a little screenshot from Tinkercad. This is what I have going right now. So the input devices, you can see here, I have a button right here connected to pin 12, reading the input from that. I have a force sensor here connected to this analog pin to read that input, and then of course the servo motor down here, which is plugged into pin 2, and that is the setup I have here. Now, as far as the general rundown of how this robot works, it's pretty simple. The robot will just read or will just detect if the requirements for the force sensor have been met, and if they have, then it will make sure that there is a signal from the table kiosk requesting a refill, and if it has, it'll travel to the table and dispense water, and it'll just continue to do that as long as those two requirements have both been met. Then it will dispense water. And on the left here, you can see the code that I've used, and we'll see it in action here pretty soon. Yeah, right. So yeah, this is what I have, the same screenshot that I had in the slide, and we can go ahead and pull up that code. You can see what I had here, as well as the serial monitor. We'll go ahead and start the simulation. And so, as I said, the force sensor, its job is just to detect if a cup has been placed. So basically, it'll just detect the weight of the cup, and if that is on the sensor, then the robot will know that it can come and dispense water. If there's a signal from the kiosk and there's no weight on the sensor, then the robot will not dispense. So both of those requirements have to have been met. So what I set it here is I just set the force um, of the cup for over 200, and so you can see on the serial monitor it climbs as I increase the force from the sensor. So we're sitting above 200 now. This button here, I have it just to I just have this button so that it can represent the signal from the kiosk. So now that we have met the requirement of the weight of the cup, if we press this button, it'll give us a 180-degree turn of the servo, and then there's a 5-second delay, and then it will come back. So yeah, as long as these requirements have been met, it'll work. If I bring this under 200 and then press the button, nothing's going to happen. But as long as we have it above and then press, we're good to go.
Hello, my name is Tom Salona. My contribution to our project was the creation of a robot which will collect dirty dishes after patrons have left. The robot will stand about 50 inches tall with a maximum reach of 60 inches. Its chassis will be constructed of a corrosion-resistant aluminum magnesium alloy, while its collection arms will be made of a lightweight carbon fiber material. A heavy rechargeable battery will be mounted to its base for both power and stability, and its wheels will be concealed behind the walls of its chassis to prevent potential injury to patrons. Its front will be mounted with a variety of ultrasonic distance sensors to assist with navigation, locating tables, and mapping out dishes. Its dish hopper will include drainage holes and spring-loaded plates, which will both detect the remaining capacity of the hoppers and prevent damage to dishes while loading. Here's a look at the algorithm the robot operates by. Upon being called for table service, it will add the table to its queue. If it detects its hoppers are full, it'll first drop off its load in the kitchen. When it's ready to proceed, it'll move forward until it detects a table within 6 inches, or a non-table object within 12 inches. If it's the latter, it'll attempt to find a valid path forward, first by turning right in 10-degree increments, and then turning left in 10-degree increments. If neither side offers a valid path, it will move backwards 5 feet, and then check its sides again. Otherwise, if it finds a table, it will immediately stop moving and proceed to map out the dishes. It will use distance sensors mounted at different heights to determine which dish is closest and which type of dish it is. It will then use the appropriate retrieval protocol for that dish and then map out the dishes again. If at any time it detects its hoppers are full, it will stop collecting dishes and return to the kitchen to drop off its load. If it has no tasks, it'll return to its charging station. Here's a peek at the circuitry and programming used to govern this robot's behavior. To begin, the obstacle sensor and table sensor will both detect the distance of the closest object in front of them. If the obstacle sensor detects no obstacles within 12 inches, it will move both wheels forward. If, however, the obstacle sensor does detect an obstacle within 12 inches, it will stop moving and attempt to find a valid path forward, first by turning right in 10-degree increments, and then left in 10-degree increments, and if all else fails, by moving backwards 5 feet and checking its sides again. If the obstacle sensor again detects an obstacle within 12 inches, it will begin its pathfinding protocol where it previously left off. If the table sensor detects a table within 6 inches, it will initiate its dish mapping protocol and cease all movement. The table mapping is performed by the rightmost array of distance sensors, which represent a lower, middle, and upper sensor as shown. If the top and middle sensor detect a distance that's further than the bottom sensor, then the robot will detect a plate using its plate collection protocol. If the middle sensor detects a distance that's closer than the bottom sensor, then the robot will detect a bowl and use its bowl collection protocol. If the top sensor detects a distance that's closer than the bottom sensor, then the robot will detect a cup and use its cup collection protocol. If the bottom sensor measures a distance above a certain threshold, then the robot will signal that the table is clear.
Hello, I'm Elijah Hoffman, and this is the table cleaning robot. So it's designed like a little cart. It's going to have 4 gear motors for pushing it forward and IR sensors for tracking its movement, as well as a scrub pad in the back and a detergent dispenser. In relation to the table, it's going to use the design on the table to track and go to the center. The detergent dispenser is located behind the scrub pad, so first it's going to go towards the center, laying detergent behind it, and then it's going to turn around and stop dispensing detergent and go back around this spiral, this time scrubbing up the detergent which was left behind in the initial first go around. So for the logic of the table cleaning robot, first we're going to set a couple variables. We're turning right first, and we have no right turns yet. Then we're going to wait for a central hub signal to start. And then once we get that signal, we're going to open the detergent dispenser and start this loop. First, if both right and left sensor sees black, this means we're at a wall. And if that's true, if the direction variable is right, which is at the beginning when we set it to right, we're going to add 1 to the amount of right turns and then turn right. If both aren't black, we're going to see if the left sensor sees black. And eventually we're going to turn right. But another conditional check in here is going to see if there's a right turn made within the last 50 milliseconds. And this is just checking if we're in the center, because at the center we're going to be turning really rapidly. And if this is the case, we're actually going to set the direction variable to the left and close the detergent dispenser. All right, we go back to the beginning, and if the right sensor only sees black, we're going to turn left. And if we pass all these tests, we're going to go forward. And then also, finally, if the direction variable is not right, meaning it's left, we're just going to iterate through the amount of right turns we calculated. Every time we turned right, we added 1 here. So we're going to just go that amount of right turns, except we're going to be turning left. And then once finally we're at 0, meaning we went through all of our right turns, we're going to send a message to the central hub stating that the table is clean. Let's take a look at the circuit design. So we have our 4 motors. These 2 front motors are used for steering, so they actually are connected separately. It's going to steer by going in opposite directions. And these two rear motors are connected together since they do not need to go in different directions. This servo represents the detergent dispenser either being closed like this or opened up and down. H-bridge motor drivers. It's important to note that I wasn't able to get the IR sensors in the front to simulate tracking well in Tinkercad, so this demonstration will use a different logic. Just for a spiral, each subsequent length is just going to be an incremental decrease from the original length. So this robot will calculate the length of the first, and then it'll just turn right and then go an incremental less length all around. And in order for it to get inputs for the simulation, I have this IR sensor here. So let's go see it in action. Here is the circuit design in Tinkercad. Let's go ahead and start. And this puts it in its idle state. By hitting play, I will simulate the central control hub telling it to go. And by hitting 6, I'll simulate the robot reaching its first right turn. So I'll do that pretty rapidly. So by hitting play, we saw that it's going forward, and this detergent dispenser is now opened. So it'll go forward, and then it'll turn right by going backwards on the right motor, forwards on the left motor. And in the serial monitor here, we see that it grows for a decreasing amount of time. And then once it hits the center, we will close that detergent dispenser and repeat the process in reverse. So it'll go in an increasing amount of time and then turn left instead of right. And finally, once we are going to drive for the 100% of the first time, we're back at the start, so we're going to stop. So the Arduino code is a little different than the logic just because of the limitations. I declare all the pins. I have a switch statement for the remote, and then the clean function will calculate the distance of the first length of the spiral, and as described before, it will just go in a decrementally less fashion, as well as just reaching the center, closing the detergent, and then heading back. And yeah, that is the Arduino code. Here is the swarm simulation. So our robots are color coordinated in either active, in progress, or heading back. And these just demonstrate the paths that all the robots are going to take. So they're going to be separated in whatever different type of robot they are. And then this middle path is going to be the exit row where each robot will exit. So let's see, this man needs some water. So the water refill robot's taking care of that. This table needs to be cleaned, so the table cleaning robot is cleaning that. These two people, one of them got a medium rare steak, and then this one got a well done steak. So the food delivery robot is going to deliver the food there. This table needs clean their dishes, so the dish collecting robot will take care of that. And over here, this customer needs some more water, so a water refill robot is on its way to make his delivery.
When it comes to robotics in the restaurant industry today, our team has found that current offerings are a bit limited. Robot servers do exist, but are often viewed as a novelty to woo customers rather than true cost savings. We propose to offer a truly holistic solution to front-end restaurant operations by creating a suite of robots that can perform the labor-intensive tasks typically performed by humans. We believe our proposal will offer restaurateurs with more consistent service quality, a more robust labor supply, and long-term savings. It is our hope that our offering will move restaurant service robots from mere novelty to necessary infrastructure and revolutionize food service operations.
Making the decision to move forward with automated restaurant staff will yield invaluable returns in the consistency of service quality and a vast reduction in labor costs. Additionally, the novelty of a robotic restaurant staff alone can increase revenue by increasing customer volume. These proof of concept designs that we've displayed demonstrate the future of the service industry. This project has really put into perspective the importance of creativity, communication, and perseverance in the engineering design process. Given the opportunity to do this again, I would only increase the amount of time I'm able to put into this project. I believe I speak for my whole team when I say it's been a joy to collaboratively create new things, and I'm very eager for more opportunities in the future.